We're going to start Chapter 5, Foundations for Inference. This section is Section 5.1, Point Estimates and Sampling Variability. We said that in statistics, we're usually interested in a large population. We want to know something about the population. And because the population is so large and it's going to take a lot of time and money to figure out the piece of information we want to know about the population, instead we usually construct a sample. So we get a group of random individuals that are representative of the population, and we try to study those individuals and draw conclusions from that sample. We draw conclusions about the entire population at large. So we said that a summary statistic was a single number or piece of data that summarizes the sample. We've talked about a lot of different statistics like mean, median, mode, standard deviation. We use X bar to represent the mean of the sample, and we use the letter S to represent the standard deviation of the sample. We're going to talk about the mean and the standard deviation a lot for the rest of the semester. So we're going to use these symbols to represent the mean and the standard deviation. Another symbol that we're going to use is p hat, which is the percentage or proportion of the sample. So for example, if you were interested in the percentage of Americans that have a TV, then we would use p hat to denote that percentage. So these are the symbols we're going to use for statistics. We're also going to use symbols for parameters. Recall that a parameter is a single number or piece of data that summarizes the population. So for the mean of the population, we're going to use mu. And for the standard deviation of the population, we're going to use sigma. So X bar is for the sample, mu is for the population, S is the standard deviation for the sample, and sigma is the standard deviation for the population. P hat is a percentage or proportion of the sample, while just P is a percentage or proportion of the population. Here's a research question. How many hours a day do Americans spend watching TV? Suppose you have a sample of Americans and you find that the sample mean, X bar, is 3.2 hours. Does that mean that for the whole entire population, the population mean is also 3.2 hours? No, they're not necessarily equal. And if the sample standard deviation is 0.5 hours, does that mean that the sample, the population standard deviation is also 0.5 hours? No, they're not necessarily equal. Why wouldn't they be equal? Some examples include the sample not being representative of the population. If you use convenient sampling, that is a problem. We usually don't have the statistics matching the parameters. Maybe there's some bias. So for example, if you ask the people in your sample to participate in a survey, but they chose not to, or some of the sample chose not to, that could result in non-response bias. Maybe you did some inaccurate measurements, the rounding is off. There could be a multitude of reasons why the statistics don't match the parameters. And any reason is considered bias. You have bias in your measurements and in your sample. Now, if there is no bias and there is no sampling error, then just pure chance could result in the fact that our statistics don't match our population parameters. Now, the assignment of values to a population parameter based on a value of the corresponding sample statistic is called estimation. We're interested in estimating population parameters. A point estimate is the value of a sample statistic that is used to estimate a parameter. So p hat is considered a point estimate. We are using it to estimate a parameter. According to the Census Bureau, 30% of American households are single occupancy. The population of interest here is all American households, and they're telling us that P is equal to 0.3. They're telling us a parameter. Now let's do a little bit of a review. Using the empirical rule, if we sample 40 American households, there is about a 68% chance that the number of single occupancy households in our sample is between what two numbers? So I said empirical rule. Remember the empirical rule? There's a 68% chance we're within one standard deviation of the mean. So we need to find the mean and we need to figure out the standard deviation. Now, the setup for this problem is binomial. Remember that if x counts the number of households in the sample that are single occupancy, this would be a binomial distribution. And if we want to convert a binomial distribution to a normal distribution, we need to make sure the sample is large. The rule for a sample being large is that n times p and n times 1 minus p are both greater than or equal to 10. So if I take n times p, 40 times 0.3 is 12, and n times the failure probability is equal to 28. Both of those numbers are greater than 10. So the next step for a normal distribution, we need to find the mean. We said the mean is just equal to the expected value of a binomial distribution. So that is equal to 12. The standard deviation is the square root of the sample size times the probability of success times the probability of failure. So we're going to put all of that into the calculator and it's about 3. So we know what the mean is and we know the standard deviation. 68% means we add and subtract one standard deviation. So if we subtract 3 from our mean and add 3 to our mean, we get the numbers 9 and 15. So there's a 68% chance that the number of single occupancy households in our sample is between 9 and 15. I'm going to change this problem just a little bit. I want to mention before I do that, that the numbers 9 and 15, we can think of them as percentages. If I take 9 and divide by 40, that will tell me that I have 22.5% of the sample. And if I take 15 and divide by 40, I'll get 37.5% of the sample. So another way I could word this is that there is a 68% chance the percentage of single occupancy households in our sample is between those two percentages. We said 22.5 and 37.5. So between 22.5 and 37.5. Now, I'm going to redo this problem, but I want to do it involving percentages. Now, we said that mu was equal to 12. Make sure you have all of the things from the last slide written down. So I'll go back just a second if you didn't write it down. Write down mu, sigma, 9 and 15, and the percentages, and double check those percentages so that you can get the same thing. Now, when I did that problem, I found the percentages at the end. Instead of doing that, I can find them in the very beginning. So if mu is equal to 12, I can divide that by the total, the sample total, to get the percentage. But we're already told in the very beginning the percentage is 0.3. So we're going to use 0.3 instead of mu. So instead of saying 12, it's the same thing as 30%. So if I let mu be 30%, and the standard deviation we said was 3, well, we could think of that as a percentage, 3 over 40, and that's 7.5% or 0.075. Then we can do the same problem by taking this true parameter, the 0.3, and adding and subtracting this 0.075, and we'll get the same answer. So whether you convert it to actual people, so if you wanted to find the number of people and at the end change it to percentages, you can do that, or you can start with mu, letting it just be the percentage of households that are single occupancy, and then taking the standard deviation and dividing by 40, you're going to get the same answer. So it depends on what the problem asks. In the future, we will be working with these percentages, so it may be easier to work with this instead of converting it to people. Let's run an experiment and see if theory matches reality. So what I'm going to do is I'm going to create a sample of people, and I'm going to use the computer to help me with this. I'm going to run a simulation. So I'm going to tell the computer that I want a sample of 40 households, and the true probability of getting a single occupancy household is 0.3. And I want to count how many households in my sample actually are single occupancy. The way we're going to do this is we're going to use a command. It's equals binom.inv. We're going to put the number of trials or the size of your sample. And then the next thing we're going to put is the true probability of success, which is 0.3, followed by rand and then two parentheses. And that tells the computer to pick random people from the population. Let's see what happens. Okay, I'm going to type equals binom.inv, parentheses. I want the computer to select 40 households. The probability of success is 0.3, and I'm going to type rand. I'm going to hit enter, and I got 12. So the computer said that out of these 40 households, 12 of them were single occupancy. If I put that into a calculator, 12 divided by 40, I got 0.3. I'm going to write that down off to the side. So I got that 30% of this particular sample was single occupancy. Now notice 30% was in that range that we found earlier. We said that there's a 68% chance that we get something between 22.5 and 37.5. Let's run it again. I can just click on this and hit enter. And this time I got 14. So it created a new sample of 40. And if I take 14 and divide by 40, I got 0.35. So in this particular sample, 35% was single occupancy, which is again in between that 22.5 and that 37.5%, that range we found earlier. You can keep running this and you can get different numbers. Sometimes it'll be close to the mean, sometimes it'll be far away. What I want to do next is I want to create a histogram of this. So when I ran this earlier, I got 13. And I can make this a percentage by using the command equals, and then I click on the cell and divide by the total. And when I had 13, I got 32.5%. So for that particular for that particular sample, 32.5% of them were single occupancy. Now, I didn't get the actual percentage, the parameter, zero point 0.3, but I was within one standard deviation. And all of the other times I ran this, I was within one standard deviation. Now, you might get something different. Maybe your answer is not within one standard deviation of the mean. It may be within two standard deviations of the mean. You may get something even further away. But if we kept running this, if we kept doing this experiment over and over again, how many times will we get something close to the mean? Well, it should end up looking like the normal distribution. Let's see what happens if we run this experiment 10 times and make a histogram of our results. I'm in Google Sheets, and you can see that I have this formula that we've been working with, and anytime I hit enter, the number may change. If I do something over here, you can see it just reruns that formula, and that's okay. I'm going to click on the bottom right-hand corner and I'm going to drag it all the way to cell A10. You can see the number changed, but it's just rerunning the formula, okay? Then over here off to the side, I'm going to type equals. I'm going to click on A1 and divide by 40 to make this a percentage. And then I'm going to just take this number and drag it all the way down to cell B10. So what we can see is that the computer has chosen 40 different households, a total of 10 times. And for each one of those samples, so for the first sample here, you can see that it found that 12 of the 40 were single occupancy. Then in the second one, 12 out of 40. Then in the third one, 11 out of 40, and so on. Let's look at these percentages. Now we said there was a 68% chance we were within one standard deviation of the mean. And that was between 22.5 and 37.5. And let's just kind of look at these numbers here. I think all of them for this small set, they're all between 22.5 and 37.5. So what I'm going to do is I'm going to click on these 10 probabilities here, and I'm going to insert a chart, and I'm going to switch to histogram. So histogram is down here under other, and I clicked on that. And this is the chart I have, which is not, it doesn't look like a normal distribution, but I only have 10 observations, right? I only ran this 10 times. Um, but we can see that it kind of looks a little symmetric. If we move that one column on the very far right to the left, it would look perfectly symmetric. Um, if we ran this more, let's see what would happen. So I'm going to delete this. I'm going to drag this A10. I'm going to drag it all the way down to 50. Okay. And then I'm going to drag B10 all the way down to 50. And now let's highlight this column and insert a chart again. Make sure it's a histogram. And you can see now it's still not perfect, but we can kind of see the shape of a normal distribution forming, right? Um, it's starting to look nice, like round. It's not perfect, but you can see that the more we do this, so let's do it one more time. Let's see if we can make 100 different samples here. So I'm going to just go down all the way to 100. And I'm going to insert a chart, do a histogram. Oops. Histogram. Okay, now this is starting to look more like a normal distribution. And the more times you ask the computer to run this, if we plot all of the different outcomes here, it's going to look better and better. So the theory is matching reality the more times we ask the computer to run this program. So here's an example of running the program 10 times with each sample consisting of 40 households. These are the different percentages I got. And then here I asked the computer to run the same program 100 times. And here I asked the computer to run the program 500 times. And each time it's starting to look more and more like the normal distribution, and that the theory is matching reality. So the histogram of our results looks more like a normal distribution each time we run the experiment. What would improve the, I had 400 households. So I ran the program, instead of using 40, I used 400, and I asked the computer to run this 2,000 times. So to find 2,000 samples, and each sample had 400 households, this is the distribution I got, which looks even better. It looks more like a normal distribution. Now, suppose the true percentage of American households that are single occupancy is 30%, but you don't know this number. Suppose the true percentage of American households that are single occupancy is really 30%, but you don't know this number. When we ran the simulation, we knew this number, and when we ran the simulation, we got this normal distribution. But let's say that we didn't know that number, okay? That's the whole goal of statistics, is to find this number. But if we don't know it, how can we find it? So we can't run a simulation. What we need to do is we need to go and create a sample. So we're going to use one of the sampling methods to get a sample of households. Let's say we get a sample of 400 households. So you go out, you get 400 American households, and you find that for this specific sample, the percentage of households that are single occupancy is 28%. How can we use this number to estimate the true p? How can we use this 28% and find that the true parameter is 30%? Repeating the survey over and over again would give us a normal distribution. So if I could afford to sample 400 American households 2,000 times, and I made a histogram of all of the percentages, like I did here, I would get something that would look very similar, and I would be able to estimate, oh, in the middle of that graph is 30%. But the problem is that would require time and money, and that's usually two things we don't want to spend. But theory tells us that with this one sample, this p hat, we should be pretty close to the true p. In fact, we should be within 68%. There's a 68% chance we're within one standard deviation. There's a 95% chance that we're within two standard deviations of the mean. If we don't know the true p and we don't have a histogram to help us, how do we measure the true p? Well, what we can do is build a range of values that capture the true p. We'll never be able to find the true p, but we can build a range, so we can cast a net. And if I tell you a range, there's a good chance that it's within this range. How do we do this? This is something we're going to go into more detail a little bit later, but I'm going to give you an overall picture. How do we do this? So we're going to go into detail later, but let's get an overall picture of it. What we're going to do is we're going to add and subtract a number from our estimate. For example, and it really is important to choose the right number. So I'm just going to throw a number out there. If I add and subtract 0.04 to my estimate, remember my estimate is 0.28. If I subtract 0.04, I get 0.24. And if I add 0.04, I get 0.32. So I get a range of values. So here's the true p, and I'm going to get a range of values. And if I choose the right number to add and subtract, then my true parameter is in that range. It'll contain the true p. But if I choose the wrong number, if my number is too small, then I may not get a range of values that contain the true p. For example, if I add and subtract 0.01 to 0.28, I'll get 0.27 and 0.29. That does not have 0.3 inside that range. You can see the little blue range that I've constructed is too small, and that's not good. So we want to figure out a number that we can add and subtract to get the right p. So we want to figure out a number we can add and subtract so that we have the true p in our range. And so that's going to be the basis of our next lecture. How do we choose the right number to add and subtract? Because we don't know the true p. The only thing we know is our p hat.